Hello, marvelous AP Calculus AB students, and welcome back to day 5. Our focus for today are on vertical asymptotes. Now, you've seen vertical asymptotes starting in Algebra 2, and hopefully again in pre-calculus. So your question might be, why are we studying vertical asymptotes again? Well, since we're still in our limits and continuity unit, then it should make sense that our daily learning objective is I can define vertical asymptotes using limits. So let's jump into it. A function which is not continuous, and do you remember what happens for a function to not be continuous, right? A continuous function would be something like this, versus a non-continuous function would be going and then there'd be a gap and then it'd continue on after. It's where you have to pick up your pencil. And we will define continuity using limits later on down the road, but for now let's just get into our basic definition of it's where you have to pick up your pencil if it's not continuous. Now the fancy way to say a function that's not continuous is we say that the function is actually discontinuous. And there are actually 3 types of discontinuities which you need to know. You've actually seen all these types of discontinuities before, but I'm not sure if we've ever actually named them. So we have 3 names of discontinuities below. Okay, one of them is a jump discontinuity. The second is a removable discontinuity, and the last is an infinite discontinuity. So let's see what you guys remember, or know, or can just guess at. So what we'd like you to do is to go through and draw 3 different graphs, and it's your choice on what the graph looks like. But your first graph needs to have a jump discontinuity. Your second needs to have a removable discontinuity, and as a hint, a removable discontinuity we talked last class is a hole. And then lastly, an infinite discontinuity. If you're not sure, give it a shot anyways, or you can just wait for a quick second when my voice comes back in, but I'd like you to pause right now, try those 3, and then we'll discuss and see how you did. Ready, set, go. All right. Well, let's just go through one at a time, and we'll start with this jump discontinuity. A jump discontinuity is exactly like it sounds, where our graph might be continuous, and I'll zoom in here, and your graph doesn't have to look like mine as long as it jumps at some point. So my graph does some little squiggly thing. Maybe there's a closed circle here. And then it's just going to jump up or jump down, doesn't matter. I'm going to have it jump up to 4, and then do whatever after. Now, this means that there is a jump discontinuity at x equals 1, and I'll remind you of that right up here. However, at x equals 1, we need to be careful because I put a closed circle at the point 1, 1. I cannot put a closed circle at 1, 4. Do you see why? Well, if I did put a closed circle there and I asked you, what is the y value when x equals 1? You might say, well, is it 1 and 4? But then that wouldn't be a function. A function can only have one output for every input. So what I'm actually going to do is just change this to an open circle, and we'd be good. You could, of course, made this one an open circle and then this one a closed circle if you'd like. It doesn't matter. You're making up your own graph, but only one closed circle for each x value. So jump discontinuity at x equals 1. All right, let's move on to our second one. We'll do the equations after. The second is a graph with a removable discontinuity. And you've seen these before as well, where our removable discontinuity might do something like so, and then I'm going to get to 2, 2, and then we'll just put a hole in here and then have the graph continue afterwards. Right? This is a removable discontinuity or a hole. You could, if you wanted, put another point up there, but it's not necessary. Right? A function doesn't have to have an output at every input. It just has to have one output for each input. All right, and moving on to our last one, an infinite discontinuity. This is the one you might be least familiar with, even though you've graphed equations like this before. An infinite discontinuity means at the discontinuity, at the place where you have to pick up your pencil, your graph goes infinitely up, or infinitely down, or even both. So for example, my graph could be over here and go infinitely up at 3, and then on the other side it could start at negative infinity and finish off doing whatever I'd like over here. Oftentimes we see this come down like so with a little dashed or dotted line. Set x equals 3, and we'd say that there is actually a vertical asymptote at x equals 3. So our 3 main types of discontinuities, jump, removable, infinite, you do need to know those names. What types of equations? Well, typically a jump discontinuity comes from a piecewise equation, right? Where you have y equals, and then you have that cool little curly brace here. And there's multiple different equations. That's why it jumps up from one to another. A removable discontinuity, and we discussed this a bit last class, comes from usually these rational type equations where maybe you have something like x minus 2 over, well, let's see, this occurred at x equals positive 2. So x minus 2, I don't know, something like this. Let's put it maybe another x up top, something like this. Sure. This would have a discontinuity when x equals 2. 2 minus 2 is 0, and you can't divide by 0. And a lot of times we'd see that occur as an infinite discontinuity. But because we're able to cancel our x minus 2 factors, then we say that this becomes removable, and there would be an open circle there. Now, I'm not saying this equation in red that I did here matches the graph up here. It does not, but it would at least match at the whole. A lot of times these are called rational equations. There are other equations that will have removable discontinuities. We'll see more today, but the most common is a rational. And then last but not least, an infinite discontinuity. Many times this is very similar to a rational, but instead of having something you can reduce, see, this occurs at positive 3, so what if I just did 1 over x minus 3? All right, at x equals 3, there would be divide by 0, which is an error at 3. And we cannot reduce the x minus 3's, so I think this will stay as an asymptote. All right, again, this is another example of a rational function. Again, there are many other types of infinite discontinuities. For example, y equals tangent of x has an infinite number of infinite discontinuities. All right, so although the functions drawn above are not continuous, some of them actually have limits which do exist. So looking at these discontinuous functions, which ones have limits that exist or not exist? Well, if we look at the limit of a jump discontinuity, just the idea of jumping up to a different y value, the limit of a jump discontinuity does not exist, right? And we would just say that the limit as x approaches a, we don't have an actual x value, we're just doing this, from the left side is not going to equal the limit as x approaches a from the right side of f of x. Easy enough. A removable discontinuity, though, does have an existent limit there, right? We approach the same y value on each side. So the limit of a removable discontinuity exists. And again, we'll justify with those one-sided limits. The limit as we approach some a value from, we'll keep it consistent, from the left side of f of x will equal the limit as x approaches a from the right side of f of x. All right, well, what about an infinite discontinuity? And this one can be pretty tricky over here, actually. I'm actually going to modify my graph and give this a second infinite discontinuity. We'll still keep this part over here. Don't worry, you don't have to erase too much. But then what I'm going to do is I'm going to have this guy go down and go back up at -1, and then over here also go up at -1. So we have two infinite discontinuities, one at -1, one at +3. And although technically it is okay to say both limits don't exist. So we can say the limit of an infinite discontinuity does not exist, right? The reason it doesn't exist is because the y value that you're approaching on either side of here is not actually a number. This goes up and up forever. You can say, but isn't that graph getting closer to positive infinity? You're right, but positive infinity is not a number. We shouldn't say getting closer to positive infinity. We should say getting infinitely large. Now, sometimes, though, we do abuse the notation with limits. And I'm going to say, kind of. It is possible, and I'm going to say possible here, it is possible and allowed to say the limit as x approaches a of f of x equals infinity, right? And so again, this is an abuse of that equal sign, because equaling infinity, and maybe I should put plus minus on here because it can equal positive or negative infinity. So equaling infinity is okay in our limit notation. Does not exist is also okay. So you could say the limit does not exist, and your justification would make sense. We don't approach a specific value. But over here on the left and the right side, both graphs are going up infinitely far. And so it would be allowed over here to say the limit as x approaches that was -1 of the function equals positive infinity. That's fine. Just beware, because over here the limit does not exist. This one is approaching positive infinity, but on the right side you're approaching negative infinity, and so you're not approaching the same spot. The one-sided limits aren't equal. So for this one you'd have to say does not exist. It doesn't matter which one you use on the AP exam, as long as you say does not exist here. You could say infinity or does not exist on this one. Does not exist just tends to be a little safer. So we're going to dive more into that later on today, since our main focus today is vertical asymptotes, and that is an infinite discontinuity. But I think that's enough for now. So let's get a little practice in. Draw a function which has two vertical asymptotes at x equals -2 and 3, and a hole at x equals 0. And then part B, vertical asymptotes often occur when a function is made up of a quotient of two other functions. A lot of times you'll see these called rational functions, though they're not always rational ones. Which function would have to equal 0 for a vertical asymptote to potentially occur, and why? So why don't you think about these two, jot down your answers, and then unpause whenever you're ready. You got this. Go. All right, you're back. I'm going to do our vertical asymptotes in red, so -2 and +3. And then there's a hole at x equals 0. I'll do that one in purple. Now you might say, well, where does that hole go? It doesn't matter, right? I'm going to put it down here at -3. This is 0, -3, right? There's a hole at x equals 0. For the rest of these, for our vertical asymptotes, you can do whatever you'd like. Didn't say anything of what the function's doing to the left, so I'm just going to have it get closer down here. And then, just for fun, I'll kind of have it do its own thing over here. Right? This limit could exist. You could say the limit's -infinity. And then, who knows, maybe it just kind of dives off over here, but then reappears up on the other side. So this limit doesn't exist because the left side is -infinity, the right side goes to positive infinity. And I think we're fine. This is still a function. It never fails the vertical line test. There's not a point everywhere, -2, 0, and 3, but still a function. Okay. And we briefly discussed this up above, so hopefully you didn't struggle too much here. The function that causes a vertical asymptote to occur is h of x, right? H of x equaling 0 would cause f of x to equal g of x divided by 0, which means that f of x does not exist. Right? So if the denominator of your function is 0, and we get it does not exist, two potential things could happen. You could end up with a vertical asymptote, an infinite discontinuity, or a hole, a removable discontinuity. And it's all dependent on what g of x is as a function. If they cancel, you'll get a hole. If they don't, usually you'll get an asymptote. You'll find, and I think I clarified this a bit up above, I just said define vertical asymptotes. You might be asked to find a vertical asymptote, and if you do, it'll be pretty straightforward. But as we'll see later on, it's not always that easy to find vertical asymptotes or to decide if they are a hole versus a vertical asymptote. So again, if you do get asked to find one, it's going to be very obvious with no tricks. But you should not assume that just because nothing cancels, there's automatically a vertical asymptote. We can assume that this causes a discontinuity. We're just not sure what type. So actually, let's get a little further into that. A vertical asymptote is sometimes known as an infinite discontinuity and occurs when the denominator of the function becomes 0, but is not removable. So let's try to create 3 examples below meeting the criteria stated. And you don't need to graph the functions, but if you have time, use your graphing calculators or Desmos and see if you're right. So here's your goal. A function with just a single vertical asymptote, with one vertical asymptote and a hole, and a function which is the quotient of 2 other functions but has no vertical asymptote. That one's a little trickier. Good luck, and unpause me once you're done. All right, vertical asymptote at x equals 1. Well, the easiest way to do this one would just keep 1 on top. We don't want anything to cancel to have that vertical asymptote. And then x, would it be -1 or +1? I think -1 will do it, because when x is 1, 1 minus 1 is 0. Easy enough. One vertical asymptote, one hole, and they didn't tell us where. So these have to be discontinuities, which are going to be in the denominator. So we'll do one in green, one in purple. My green one, I'll do x minus pi. Why not? So there's going to be a vertical asymptote at pi, and then we need a whole, and let's do it at x plus e. Right? E is again that 2.71, so on and so forth, a little bit bigger than 2, smaller than 3. If we want that to be a whole, though, I'll need that to cancel out, and so I'll need the same factor in the numerator. You technically don't need parentheses up here because there's just an invisible 1 multiplying. I always like to put it, though, just so we can see we can cancel, because there's multiplication in the middle. Last but not least, a function which is the quotient of two other functions but has no vertical asymptotes. Well, the numerator is pretty easy. I'll just put a 1. But no vertical asymptotes, and we need another function down here. Let's assume that we need an x. Well, I think if that's going to happen, then the denominator can't equal 0. If the denominator isn't going to equal 0, then maybe we could say the denominator is either always negative or always positive. And it's actually very easy to make something always positive, right? We could just do x squared. That turns something into a positive. But I think that has a vertical asymptote, right? If x is 0, it's 1 divided by 0. So this is positive, but let's make it bigger than 0. How can we make this bigger than 0? What about just adding 1? Right? 1 over x squared plus 1. Any real number you substitute in here will get turned into 0 or a positive, and then you add 1, so it can never be 0. Right? If you wanted to check that, you're like, ooh, but I bet x squared minus 1 could equal 0. I'm just going to subtract 1 and take my square root, and I learned in Algebra 2 that the square root of negative 1 is just I. You've done nothing incorrect here. However, two important pieces to note. First, on the real plane, the x comma y coordinate plane that we graph this in, you won't be able to see these, and these are technically vertical asymptotes, you won't be able to see the vertical asymptotes because I is not on our xy plane. And second, and here's a real fun one for you, in AP Calculus, we never deal with imaginary solutions. So if you go to solve something, you get something imaginary, it's going to mean one of two things. One, and this is probably the more common, you did something wrong. Or two, if it's imaginary, then the answer that they're looking for is no solution, or no x-intercepts if you want. But either way, this certainly has no vertical asymptotes that we can see. All right, I think we're far enough now that we can go ahead and define our vertical asymptotes with limits. In fact, vertical asymptotes are often known as infinite limits because of the following definition. If the limit as x approaches a of f of x equals positive infinity, or the limit as x approaches a of f of x equals negative infinity, then x equals a is a vertical asymptote. Now, it is important to note that the limits above can actually be a one-sided limit as well. So it doesn't have to be from both sides, right? This could actually just be from the positive side or the negative side. And it's, of course, the same thing over here. So as long as you take any sort of limit and you get an answer of infinity or negative infinity, that automatically indicates that there is a vertical asymptote at that x value. Now again, and I've mentioned this before, the hard part with vertical asymptotes is they're not always easy to see. For example, you might look at this function and say, oh, where does this have a vertical asymptote? And you might say, oh, well, that's pretty easy. X minus 1 equal to 0, add 1 to both sides, means x equals 1 is the vertical asymptote, or the infinite discontinuity. But if you look at the graph on Desmos, I should have this prepared, at x equals 1, that's right here, there is certainly not a vertical asymptote, right? There is a limit that looks like it approaches 1. So what happens there? Well, there's actually a hole. Now, the question you might have is, why is there a hole there? Like, you can't simplify natural log of x over x minus 1. Well, it actually turns out you can. There is a factor that you can reduce. And now you're probably looking at this with crazy eyes thinking, how does natural log of x have an x minus 1 that you can reduce? And my answer to that is, come back to AP Calculus BC. where we start to rewrite these functions using infinite series. We call them power series. And what's going to end up happening is the power series is going to have a common factor of x minus 1s. And you'll actually be able to reduce this and see that that drops out. So that is a pretty cool application and some foreshadowing of things to come next year. But for now, we really need to take it as just a word of caution that even if it looks like something doesn't cancel, we can't assume that that's a vertical asymptote. So they would never, by the way, ask you on the AP exam, is there a vertical asymptote? Or, what sort of discontinuity happens at x minus 1? That wouldn't be a question. That's not within the scope of this class. You wouldn't know how to see that. So if they asked you something, right, they might ask you something like this example 2 down here. They'd give you this combination, this rational function, and say, where does the vertical asymptote occur? You need to know how to do that. But once you start combining other functions, don't stress it at all. Okay? So, blah, 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 blah. Here we go. The concept behind removable, by the way, is really that you can add in a single point that causes our function to be continuous. So you can even see that up above here, right? If I look at this, if I added in a single point at x equals 0, is that now continuous? Yes, yes it is. So that's really the definition of removable, right? We can add in a single point and it becomes continuous again. In the case of natural log of x over x minus 1, you could add in the point 1 comma 1, and if there was a closed point there, now this function would be continuous. So we'd say at x equals 1, there is a removable discontinuity. It doesn't even matter that you don't know how to simplify it. All right. Another way to phrase a removable discontinuity is that the limit as x approaches a equals some number, which isn't equal to the value at a. So basically saying the point is not equal to the limit. All right, so let's get to some actual practice problems. In AP Calculus, you're expected to know the definition of a vertical asymptote using limits, but you're not often, but sometimes you will be, asked to find where an equation has a vertical asymptote. So let's look at example 1 here. You are given the graph of f of x to the right. Write a limit statement that justifies why f has a vertical asymptote at x equals 2. Right? You're looking here, and you might even think, well, there isn't a vertical asymptote, right? There's a point right at 2. But the definition of the vertical asymptote isn't what happens at 2. It's what happens as you get close to 2. It's defined using limits. And so you might look over here and you might say, but the limit doesn't exist, right? As you do the limit, as x approaches 2 from the left side, right? That's this piece right here. From the left side of f of x, that equals 3. But then, when you do the limit as x approaches 2 from the right side of f of x, that's this piece over here, that equals positive infinity. And so the limit doesn't exist. And you're right, the limit doesn't exist. But remember our definition of a vertical asymptote. As long as one limit, even if it's a one-sided limit, equals infinity, then there is a vertical asymptote. And so, because this equals infinity, that implies that x equals 2 is a vertical asymptote, or an infinite discontinuity. All right, let's try example 2. Without a calculator, identify the location of the vertical asymptote. And can you justify your answer with a limit? Why or why not? So go ahead and try this one. See if you can determine where the vertical asymptote is and write a limit statement for it. Ready, set, go. All right, you're back. Well, the first thing I'd do is I'd probably try and factor this. This is a difference of squares, x minus 2 times x plus 2. And then this guy down below, okay, 2x and x. I know there can't be a 2 in here because we'd have a common factor which isn't allowed. And the only way to multiply to make negative 2 or to multiply to make 2 is 1 times 2. Couldn't be 2 and 1 because there'd be a 2 there. Then we just have to figure out the negative and positive. This is big, so I bet positive 2. 2 times 2 is 4. Minus 1 is 3. That looks pretty good. Excellent. All right. So if we went through and looked at it like this, do you see where the vertical asymptote's going to be? Well, it's not going to be here. That is a removable discontinuity or a hole. I think it's got to be this other guy, right? 2x minus 1 equal to 0. When 2x minus 1 becomes 0, the whole denominator is 0. We can't reduce that. Let's solve it though. 2x equals 1, divide by 2. X equals 1/2 is going to be my vertical asymptote. All right, now how do we explain that to someone? Well, you might say, oh, that's easy. That's because the limit as x approaches 1/2, right, as we get closer and closer to 1/2 of our function, which is called g of x, almost wrote f of x here, equals infinity. All right, there's my statement. But is that true? Do you know that the function goes to infinity? Let's check this out. All right, I have this ready to go. Here is our 1/2, right, 0, 1, 1/2. You can kind of see that vertical asymptote going up and down here. Yeah, I think this statement is actually false. That's not true because we approach two different sides, or two different values. As you approach from the left, g of x does go up to positive infinity. But as you approach from the right, we go to negative infinity. So from here, the only correct statement for the limit as x approaches 1 of g of x is does not exist. Now, you could have gotten does not exist just by seeing that the bottom becomes 0 and the top is a constant. That would be okay. But you might say, well, wait, you asked us to define this with a limit. It is possible to do with a limit. The limit as x approaches 1/2, let's look back at that graph again, from the left side is positive infinity. Okay? Or you could have said, that was enough to justify a vertical asymptote, by the way, the right side of g of x actually ends up being negative infinity. But my question to you is, could you have determined this without a calculator? And the answer is probably not easily. You could have tried to graph this by plugging in a whole bunch of values around 2 and seeing what happened, but that's pretty tedious. So just a word of warning. It's important to note that although sometimes you can write a limit equals infinity, like these guys, the safer answer is just to write does not exist for a limit, right? Because sometimes saying infinity is just wrong, and you have to say does not exist. So if you got something up here, they wouldn't ask you to justify this with a limit because you don't know what the graph looks like. It's too complicated. You still need to be able to determine that there is a vertical asymptote there, right? That this makes the denominator become 0, rather this does, and it's non-removable. But they wouldn't ask for a limit there. If they did, the right answer for the limit would be does not exist because we don't have a way to figure this out without a calculator. All right, one last example that goes further to show you can't judge a function by its cover, or rather predict an asymptote from the denominator. Okay, so we'll let f of x be this function defined below. So without using your calculator, let's go ahead and find the limit as x approaches -3. I think the smart way to proceed is direct substitution. That's what we're usually supposed to do, right? So let's replace f of x with its actual function, and then let's go ahead and substitute in -3. Now we have these cool bars here. We hopefully remember those bars are called absolute value. Absolute value measures the distance between a number and 0. Distance is always positive, so we really say that absolute value turns any number into a positive. And the positive version of 0 is just 0, and we get 0 over 0. Well, that's unfortunate, because now we've lost a point on our free response. We have these equal signs over here. We don't want that. Let's get rid of that equal sign. Okay, this, what we did here, is equal to f of 0. F of 0 would mean just replacing the x's with 0 and finding the answer. And f of 0, because of the 0 over 0, does not exist. There is no point at 0. We tried to use our shortcut from last class, got a 0 over 0 situation, and so for a limit, this means we need to do more, right? 0 over 0 doesn't mean the limit does not exist. It's indeterminate, and so we need to do more. But the issue here is the do more. All we learned last class was factoring. We said do more means factor. But we don't know how to factor that. Now you might be tempted to say the absolute value of x plus 3 over x plus 3, absolute value makes the entire inside positive, so we can just write x plus 3 over x plus 3. Absolute value doesn't work that way. Yeah, what you just tried to do is really distribute the absolute value to each of those. And as you'll find, and hopefully you've already found, distributive property is a shortcut that actually doesn't work very often, right? It'd be the same if you were doing x plus 3 squared and you said, ooh, that's the same as x squared plus 3 squared. No, it's not. That's one of the most famous math memes out there. That kills puppies. We cannot do that. You are not allowed to distribute a square with addition and subtraction the same way that you cannot distribute an absolute value. So that is not true, because you might have tried to do that and said, oh, we can just cancel this and say it's 1, right? Something over itself is 1. Nope. So we actually don't know how to do more at this point. And so we're actually going to go back to our old friend graphs and tables and use that as an assist. Without a calculator, we're going to find the value of the limit in part A, and we're going to do it by creating a graph from the table. So what I'd like you to do is there are 5 values here. We've already done one of these, right? We already did -3 up above. We found that f of -3 ends up becoming does not exist. Right? We did that up here. So what I'd like you to do is to find f of -5. You might have to write a little bit small here, but you'll be all right. F of -4, f of -2, and f of -1. And I'd like you to do that without a calculator. You should be able to do some basic addition, subtraction, division, absolute value without a calculator. So give that a shot. Let's see what you get. And if you're feeling particularly bold, you can go ahead and graph those points over there and see what your graph's going to look like. Ready, set, go. All right, you're back. Let's try each of these. I'll start down here at the bottom of the table and work my way up. So we're going to do the absolute value of -1 plus 3 over -1 plus 3. We need to work from the inside out here. 3 minus 1 is 2, and the absolute value of 2 stays 2. 2 divided by 2 is 1. So what we found here is the point, and I'll just put it over here. -1 was the input, 1 was the output. -1, comma 1. Then we try f of -2. -2 plus 3 over -2 plus 3 is the absolute value of 1 over 1. That's 1 over 1, which is just 1. All right, so we input -2, we got 1. Now you might be thinking at this point, wait, you told us we couldn't reduce this into 1 before, but we're getting 1 every time. Why couldn't we do that? Well, let's try f of -4 and see what happens here. -4 plus 3 divided by -4 plus 3. This becomes the absolute value of -1 over -1. It becomes +1 over -1, which is -1. We got a different answer here. Okay? And so this gives us an input of -4 and an output of -1. -4, -1. Now, do you see why that is? It's all about the denominator. It's strangely not about the absolute value part. Our denominators down here were positive. We know the numerator will always be positive. The numerator is always positive. The denominator, when you use numbers that are bigger than -3, right? -2, -1, 0, those are all bigger than -3. That gives us a positive denominator. Positive divided by a positive is a positive. But when we get into numbers smaller than -3, -4 plus 3 gives us a negative, and now we're dividing by a negative number. Let's see if that happens with -5 as well. -5 plus 3 over -5 plus 3, that becomes -2 over -2, which is +2 divided by -2, which is again -1. So an input of -5 gave us an output of -1. So let's see if we can fill in the rest of this graph. It seems like 3 is kind of like that divider, right? Now I'm going to erase this wall in a second because it kind of looks like an asymptote here, and I'm not sure if it's an asymptote yet. So let's try some numbers that are smaller than -3. -4 was -1, -5, -6, -7, -8. What about -3.5? Well, that's smaller than -3. That'll make the denominator negative. -3.1, that's smaller as well. Right? It looks like as we get closer to -3 from the left, we are approaching -1. And so we can actually write that out as a limit. The limit as x approaches -3 from the left side of f of x looks like we're approaching -1. And I'll actually go ahead and put that in. But right at -3, there's no point. So to show that we kind of stop right there, we're going to put an open circle. I'll actually redo that, make it look a little nicer. we're going to show we can't actually have a point at negative 3. We got does not exist. But as we approach negative 3, we sit right at negative 1. What about the right side? Well, numbers bigger than negative 3, like 0, would cause the denominator to stay positive, stay positive, stay positive. Negative 2.5, that's bigger than negative 3. Negative 2.9 bigger. I think as we approach from the right side, we're approaching positive 1. We're actually at positive 1, but we still use that approach terminology. So we'd say that the limit as x approaches negative 3 from the right side of f of x equals positive 1. And we can again fill that in, open circle here to show that we never quite get there. And we look at something like this. Okay? So if we're looking at these two and we have two one-sided limits that are not equal to each other, we can throw in a not equal right here, right? What type of discontinuity do we call this? I think we even defined this back on our first page, didn't we? We said that if the two one-sided limits aren't equal, then we called this discontinuity a jump discontinuity. This is not a vertical asymptote, right? So we're actually going to put two things here. First, we're going to say not a vertical asymptote. Sometimes people ask about abbreviating on the AP exam, like what abbreviations are allowed? And the answer is, as long as the reader can understand what you're trying to say, you can use any and all abbreviations. Now, if you said not a vertical asymptote, that's not an abbreviation, right? Maybe it is, you made it up, but it's not something someone else will know. But I put vert, I'm pretty sure we'll know that's vertical. You could probably have gotten away with like ASCII or something like that, but it's really as much or as little as you'd like to write as long as it still makes sense. So not a vertical asymptote because, common abbreviation, right? Because no limits equal infinity, right? So the one-sided limits, so I'd say neither one-sided limit equals infinity. That's our definition. One of them had to be infinity. Neither was. It's not a vertical. So what kind of discontinuity is this then? This is a jump discontinuity. How do we prove it? Well, we say because the limit as x approaches negative 3 from the negative side of f of x is not equal to the limit as x approaches negative 3 from the positive side of f of x. Right? They're not equal to each other. That's an easy way to justify a jump discontinuity. So here's our quick conclusion. When you find the indeterminate form for a limit, in the past, our do more was always factoring. However, if you're at a standstill for a function you don't know how to factor, don't forget you can always fall back on graphing or just creating a table. And I'm telling you right now, this question, maybe with like one different number here, is going to be on your topic 1 exam. It's going to be there. And so you might even want to say on your exam. Okay, so you're going to have a homework problem like this, a knowledge check problem like this, and it'll be on your test. And still I get students on the test who go, I don't think I ever learned this. Well, I understand because you're learning a lot. You have learned this. Be careful. It's going to be on your test. All right. The last part of today is a pretty quick one. We have done this a little bit before, and we're going to continue with it. We're going to sketch some graphs that fit some various criteria. Okay? For each question below, sketch a function that meets all of the criteria given. So my one function over here needs to meet all of these requirements, and so on and so forth down below. Let's go ahead and try the top one together, then you guys can try the other two. As mentioned before, I always like to start with the points. F of 2 equals 0, that's the point 2, 0. F of 3 does not exist. If a point doesn't exist, either there's a hole there or some sort of asymptote, so I'll leave that one blank for now. The limit as x approaches 3 of f of x equals negative 1. So 3, negative 1, and that's the limit. The easiest way to deal with a limit is to put an open circle, and then we can change it from there. If it's going to equal negative 1, though, we have to get closer to negative 1 on both sides. All right, so we took care of the limit here. Let's go ahead and look at what happens with f of 3. They said f of 3 does not exist, and I think we've done that well. We put a hole there, Nice, nothing too bad. I'll remind ourselves that's what we did. Again, there could have been an asymptote, but because the limit approached the same spot on each side, that becomes a removable discontinuity, a hole, and we're good. Looking at the limit as x approaches 2, they said that does not exist. Well, we already have this right side limit over here, so to make the limit not exist, I think the left side limit needs to go somewhere else. Now, being very careful, these are pretty close together here. This is approaching 1. So I'm just going to go ahead and say, let's see, as we approach 1 from the left side, it's infinity. It doesn't exist. I'm going to go ahead and make this one go down here, and I'll show you why in a second. So I've got this little piece right here. Okay, so I think, though, that definitely takes care of the limit not existing. Right? Left side, right side at 2, two different places. So now let's go ahead and tackle the limit as x approaches 1 from each side. So as we approach from the left side of 1, so here is the left side of 1, we need to go to positive infinity. That's not too bad. We just go up, up, up to positive infinity. As soon as we see that infinite limit, we can put in our vertical asymptote. Nice. So we took care of that. But then the right side says the limit as x approaches 1 does not exist. Now, there are a few ways that you can do this. Option 1 is it would be okay to do this. This is a limit that does not exist. However, you could also accept the argument that that limit equals infinity, the same way we did it over here. So just to be on the safe side, I'll make it go a different direction. You could either make it go down to negative infinity, and that is certainly a limit that doesn't exist, or you could be really bold and say, I'm just going to make it approach a point right here, and that's allowed as well. That is a limit that doesn't exist. I'm not as particularly a fan of that, so I'm just going to have it drop down. I just think it looks nicer, but it's up to you, and that tackles the last part. I am going to go ahead and continue this guy out just to put an arrow. You don't have to. The function could actually stop there, but I like the arrows at the end. All right, so now that you get the idea, why don't you try problems 2 and 3? A lot of my students have a nice time doing this with dry erase markers so they can erase parts and put them back together. And you'll notice that I did mine one part at a time. You can pick any part to start with. So try problem 2, problem 3, and then unpause, and we'll see how you did. Ready, set, go. All right, and we're back. So if we're looking at problem 2, I'll do the points first. G of -1 is positive 2. G of 0 is negative 2. And G of 3 is 0. Look, we're already halfway done. That's exciting. Now, as we approach 1, right, from both sides, it better be negative infinity. As soon as we see infinity with a value, we can put our nice little dashed line for an asymptote, and we need to be approaching negative infinity from both sides. So from here, I'm going to go down to negative infinity, and I don't see any other 2's on here, so I think this one we can drop down to negative infinity as well. Excellent. Then, as we approach 4 from the left side, we have negative infinity. I see a number in infinity, so 4 also gets an asymptote. As we approach from the left side, we better be going to negative infinity. Here's the left, here's negative infinity. Okay? And as we approach from the right side, we better be getting closer to positive infinity. So the right side, positive infinity. There we go. And then what about this weird gap over here? Well, it's not covered by anything else, so let's just kind of do whatever the heck we want and connect those over, and we're set. Nice. Last one. Different axis, we go all the way out to 10 this time. You can see our x values get larger, and we've got some kind of run-on equal signs here too. The limit as x approaches 2 from the right side is the same as the value at 2, and that should be 1. So 2, 1, and that's as we approach from the right side. I'll just put that little part right there to remind us what's going on. That takes care of this. The limit as we approach x from the left side of 2 is 0. So as we approach from the left side over here, we better be getting closer to 0. We need an open circle there. 2 closed circles would not make a function, or make this not a function. That would be bad. And now we move on to our third one. The limit as x approaches 6 of h of x is the same as the point at 6, which is -1. So, and it has both sides here too, doesn't it? So I need to grab, oh, whoops, I probably should have done the 4 next. Oh well. So that's important that I looked ahead. Looks like -1 from both sides. I'm just going to do that. Could have curved them either way. And now we're going to jump back to 4. Oof, almost missed that one. As we approach 4 from the left side, it's infinity, right? 4, infinity. And so that means we automatically have an asymptote. Now we're only looking at 4 from the left side getting closer to infinity. So my left side over here, so we're getting closer to positive infinity, something like that. And there's nothing that talks about 4 from the right side. So we could do anything we want to fill in that gap. You could have it go to negative infinity. You could, and let's just have it kind of go over and sit at a point here just to remind you you can do that. Nothing wrong with there. So yeah, looking good. Let's go ahead and take a look at 8. So as we approach 8, the limit is not equal to the point. So this limit at 8 needs to be in some other spot than the point at 8. So let's do the limit first. So I'm going to get closer to an open circle up here, and I'm just going to make the limit do its own thing. We do have 9 coming up, so I'm going to kind of just do a small little piece here. And then the point at 8 can't be in the same spot, so let's just make a point, I don't know, down here. Wherever sounds good to you. And now the limit is approaching 2, but the point is at -3. And last but not least, 1, 2, 3, 4, 5. I think I have to repeat a color. Oh, it's all right. As we approach 9 from both sides, we need to get closer to negative infinity. 9, infinity. We know that there's an asymptote. And from both sides, we're getting closer to negative infinity. So here, and then something like that. All right, I think we're looking a-okay here. We've finished this off. We have a good idea of how to graph functions based on criteria. The downfalls or the pitfalls of assuming that something is a removable discontinuity, or even up here that there is an asymptote there, right? We do know that we need to be comfortable with rationals and able to identify a vertical asymptote. We have a definition of the vertical asymptote. Anytime your limit, any type of limit equals some sort of infinity, vertical asymptote there. And we know our 3 types of discontinuities: jump, removable, infinite. We'll focus more on these as we move through the next few days, but hopefully this was a nice introduction to discontinuities and vertical asymptotes.